It's used down into a category of insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory it's useful to pretend like all materials in the universe can be broken down into a category of insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory physics classes and problems and tests, you can get pretty far assuming that it's either an insulating material electrically or a conducting material electrically. And before I talk about the differences between these, here I have two solid cylinders of either an insulating material or a conducting material. Before I talk about the differences, one similarity is that both insulators and conductors are composed of a huge number of atoms and molecules, and these atoms and molecules, whether it be insulator or conductor, are composed of a positively charged nucleus and a negatively charged swarm of electrons that surround that nucleus. Another similarity is that for both conductors and insulators, the positively charged nucleus cannot move. I mean, it could wiggle around and jiggle just from thermal vibrations, maybe a little bit in place, but it can't travel freely throughout the material. For either an insulator or a conductor, as long as it's a solid, if it was a fluid, I suppose these things could move and migrate around, but for a solid, the positively charged nucleus is fixed. They're stuck. The thing that might difference, there are electrons in a conductor that can move about relatively freely. These can move around with almost no resistance. Whereas for insulators, the key difference is that these electrons cannot move around freely. These don't have the right energy levels and bands in order to make these electrons move around freely. They're also stuck. For insulators, everything's basically stuck. These electrons might be able to jump around in their own atom or get shared with a neighboring atom, but it can't jump around freely from atom to atom and travel throughout the insulator. For the conductors, the electron. It's useful to pretend like area of insulator, or electrical conductor. Now that's not completely true. There are semiconductors and superconductors and other exotic forms of electrical materials, but for most introductory physics classes and problems and tests, you can get pretty far assuming that it's either an insulating material electrically or a conducting material electrically. And before I talk about the differences between these, here I have two solid cylinders of either an insulating material or a conducting material. Before I talk about the differences, one similarity is that both insulators and conductors are composed of a huge number of atoms and molecules, and these atoms and molecules, whether it be insulator or conductor, are composed of a positively charged nucleus and a negatively charged swarm of electrons that surround that nucleus. Another similarity is that for both conductors and insulators, the positively charged nucleus cannot move. I mean, it could wiggle around and jiggle just from thermal vibrations, maybe a little bit in place, but it can't travel freely throughout the material. For either an insulator or a conductor, as long as it's a solid, if it was a fluid, I suppose these things could move and migrate around, but for a solid, the positively charged nucleus is fixed. They're stuck. The thing that might be able to move are the negatively charged electrons, and here's the difference. There are electrons in a conductor that can move about relatively freely. These can move around with almost no resistance. Whereas for insulators, the key difference is that these electrons cannot move around freely. These don't have the right energy levels and bands in order to make these electrons move around freely. They're also stuck. For insulators, everything's basically stuck. These electrons might be able to jump around in their own atom or get shared with a neighboring atom, but it can't jump around freely from atom to atom and travel throughout the insulator. For the conductors, the electrons can do this. That's the key difference. Now, the electrons aren't going to just do this on their own. They'd have to be compelled to start moving by hooking this up to a battery or setting up some sort of electric field or force. And if that did happen, then the electrons in a conductor could start migrating down the line. But in an insulator, the electrons are stuck, which might make you think that, well, okay, shoot, for electrical materials, all we really care about are the conductors. The insulators we just use if we don't want electrical interaction. And while that's somewhat true, it's not completely true. Because if I set this insulator up to a battery, or I set up some sort of electric field or force in here, even though the electron in an insulator can't jump from atom to atom, what it can do is it can shift. This nucleus and the cloud of electrons can kind of shift a little bit. Positive maybe this way, and then the negatives over on the other end. So what you'd get is that overall, this side of the atom would be more negative, and this side of the atom would be more positive. And even though the electron doesn't move, and the electrons don't move, now, because this is set up where the positive is shifted from the negative, this material, if you get all of them to do this, or a lot of them, this can create an overall electrical effect where this insulator can interact with other charges nearby and exert forces on them. So even though the charges can't flow through an insulator, they can still interact electrically. Now, let's see what happens if we add extra charge to these insulators or conductors. I mean, the way they started off right here, we had just as many positives in the nucleus as there are negatives surrounding them, and that's true for the conductors and insulators. What happens if we add extra charge? Maybe we add extra negatives into here. Then what happens? Well, it'd get really messy if we tried to draw it with all the atoms. So since these all cancel out their overall charge, I'm not going to draw every atom and nucleus. I'm going to just pretend like those are there and they're all canceling out. I'm just going to draw the actual extra charge. So let's say we added extra negative charges to this insulator. What would happen? Let's say I just add a negative charge here and a negative charge there and here and there, and I've added a bunch of negative charges to this insulator. What would happen? Well, we know these negatives can't move throughout an insulator. Charges can't flow through an insulator, so they're stuck, which means for an insulator, I could charge the whole thing uniformly if I wanted to, where the charges spread out throughout the whole thing. Or I could make them bunch up on one side if I wanted to, and they'd be stuck there. But the point is that they're stuck. For a conductor, what would happen? If I tried to put a negative here and a negative there, some extra negative charge on a conductor, they don't have to stay here if they don't want to, and if you put extra negatives in here, they're not going to want to because negatives repel each other. Just like opposites attract, like charges repel. So what are they going to do? Well, this negative is going to try to get as far away from the other negative as it can. It's going to go over here. This negative is going to try to get as far away as it can. It repels it. Now, it can't jump off the conductor. That takes a lot more energy, but they can go to the very edge, and that's what charges do for conductors. If you got a solid conducting material, you put extra charge on it, it's all that charge is going to reside on the outside edge, whether you've added extra negative or positive, always on the outside edge. So you can only add charge to the outside edge for a conductor, because if it wasn't on the outside edge, it'll quickly find its way to the outside edge because all these negatives repel each other. And I said this is true for positives or negative. You might wonder, how do we add a positive? Well, the way you add a positive is by taking away a negative. So if you started off with a material that had just as many positives as negatives and you took away a negative, it's essentially like adding a positive charge in here. But again, the net positive charge, the net negative charge always resides on the outside edge of a conductor because charges try to get as far away from each other as possible. So what physical materials actually do this? What physical materials are insulators? These are things like glass is an insulator, wood is an insulator, most plastics are insulators. All of these display this kind of behavior where you can distribute charge and the charge can't flow through it. You can stick charge on it. In fact, you can stick charge on the outside edge and it would just stay there. And there's conductors. These are things like metals like gold or copper is typically used because it's kind of cheap, cheaper than gold certainly, and or any other metal, silver works very well. These are materials where charges can flow freely through them. So now that we see how conductors and insulators work, let's look at an example. Let's say you had two conducting rods. Say these are made out of metal, and one of them has a net amount of negative charge on it, which is going to reside on the outside edge, because that's what net charge does on a conductor. But this other rod, this other metal conducting rod, does not have any net charge on it. What would happen if I took this first rod, touched it to the second rod? You could probably guess, charges want to get as far away from each other as possible. So these negatives realize, hey, if we spread out, if some of us go onto this rod and some of us stay here, we can spread out even farther away from each other. That's what they would do. If these rods were the same size, you'd have equal amounts on each. If the second rod was bigger, more of them would go onto the second one because that would allow them to spread out even more, and some would stay on the smaller one. So that's charged by just touching something. That's easy. You can charge something also. You can get clever. By induction, it's called. And what does this mean? Charge by induction says, all right, first imagine I just take this and I bring it nearby, but don't touch it. What would happen? Well, there's negatives in here. I haven't drawn them. And there's positives in here. The negatives can move if they wanted to, do it as far away from them as possible. So even though there are already some negatives here, a net amount of negatives are going to get moved over to this side. So they were located with their atom on this side, but they're going to want to get away from this big negative charge, so they move over to here, which leads, i.e. there's a deficit of electrons over here. So this side ends up positively charged. And happened, yeah, because now these positives are closer to the negatives than the negatives are, and these positives in this charged rod are attracting these positives. These negatives in this conducting rod are attracting these positive charges because like charges repel and opposites attract, but they actually don't. This would cause this rod to get attracted to the other rod, so that's kind of cool. This means if you took a charged rod, brought it to an empty soda can, let that can sit on the table in this orientation so it could roll. If you bring the rod close, the can will start moving. That's not charged by induction. Charged by induction is something more. It says, all right, take this piece of metal and conduct it to ground. If you took a big metal pipe, stuck it in the ground, that would count. Or any other huge supply of electrons, a place where you can gain, steal, basically take infinitely many electrons or deposit infinitely many electrons, and this ground would not care. So the frame of your car, the actual metal, is a good ground because it can supply a ton of electrons or take them. Or a metal pipe in the earth, some place you could deposit electrons and take them, and that thing won't really notice or care. Now what would happen if I bring this negative rod close to this rod that was originally had no net charge? Now, instead of just going to the other side of this, they say, hey, I could just leave. Let me get the heck out of here. These negatives can leave. A whole bunch of negatives will start leaving. And what happens when that happens is that your rod is no longer uncharged. It has a net amount of charge now. They won't all leave. You're not going to get left with no electrons in here. There's going to be some electrons in there. But some of the electrons will leave, which means this rod, which used to be uncharged, now has a net amount of positive charge in it. So I've charged this rod without even touching it because I let those negative electrons leave. And if I'm clever, what I can do is I can just cut this wire before I take away the thing that induced the charge. If I remove this now, move it far away, what these negatives would have done is they would have said, phew, okay, I'm glad that's over. Now I can rejoin. I'm attracted to this positive again. I'm going to rejoin my positive, and this thing would become uncharged again, but now they can't get back. They're stuck. There's no way for these to get back because you've cut the cord here and you've permanently charged this piece of metal without even touching it. It's called charge by induction. It's a quick way to charge something up. But let me show you one more example. Everyone's tried this. You take a balloon. What happens? How do you charge it up? You rub it against your hair. It steals electrons from your hair and the balloon becomes negatively charged. What do you do with it? You know what you do with it. You take this thing, you put it near a wall or a ceiling, and if you're lucky, it sticks there, which is cool. How does it work? Well, remember, this is an insulating material transferred, but even in an insulating material, the atom can reorient or polarize by shifting. The negatives in that atom can shift to one side, the other side becomes a little more positive, and what that does is it causes a net force between the ceiling and the balloon because these positives are a little closer. So these positives are attracting the negatives, and the negatives are attracting the positives with a little bit greater of a force than these negatives are repelling the other negatives in the ceiling. And because of that, because the ceiling is also attracting the balloon, and the balloon is attracting the ceiling with greater force than the negatives are repelling the balloon can stick because of the insulating material's ability to polarize and cause an electric attraction. This is what I said earlier. Even if it's an insulator, sometimes it can interact with something electric because the atom can shift and polarize.
La electrónica en menos de un siglo ha avanzado con tanta rapidez gracias.
The word semiconductor is widely known and used around us. But what is a semiconductor? It is not something that you can readily buy in a store. Also, only a small percentage of people that watch my videos are actually subscribed. So if you end up liking this video, consider subscribing, it's free, and you can always change your mind in the future. Enjoy the video. Before we can talk about a semiconductor, first, we need to know about a conductor and an insulator. A conductor as its name implies, is a substance that conducts electricity. In order to conduct electricity, electrons need to move around because protons and neutrons are bound in the atomic nuclei. The electrons in the outermost shell of an atom are called valence electrons. Now, these valence electrons in a series of energy level form an energy band called a valence band. From the valence band, electrons can jump into an empty band of electron orbitals called a conduction band. In a conductor, there is no gap between the valence. They move from the valence band to the conduction band. This movement of electrons creates an electric band is a substance that does not conduct electricity. Unlike conductors, insulators have a large gap between the valence band and the conduction band. Valence electrons cannot reach the conduction band, therefore no electricity flows. Finally, let's talk about a semiconductor. A semiconductor is a substance that has properties between an insulator and a conductor. There is a gap between the valence and the conduction bands. However, it is small enough so that the valence electrons can reach the conduction band when the energy is provided by an applied voltage. The most widely used Silicon Valley in California. Silicon atom has 4 valence electrons, so each silicon atom can bind to 4 other silicon atoms. This way, all of the valence electrons are used to make a bond with other silicon and they cannot move around. Now this makes a pure silicon crystal an insulator rather than a conductor. To increase conductivity of silicon, tiny amounts of impurities can be added before silicon crystallization. Now this process is called doping. Depending on the impurity that's introduced to silicon, it can be classified as N-type semiconductor or P-type semiconductor. If an impurity atom has 5 valence electrons, such as phosphorus, 4 valence electrons can bond with 4 adjacent silicon atoms, and the 5th electron has nothing to bind to, so it's free to move around. This creates extra electron energy levels. Now, electrons can easily jump into the conduction band when the energy is called N-type semiconductor. N-type refers to the negative charge of the extra electron. If an impurity atom has 3 valence electrons, such as boron, it then binds with 3 adjacent silicon atoms and forms a hole where the electron of the 4th silicon has nothing to bind to. This positive charge, electrons from the when the energy is provided by an applied voltage. This is called P-type semiconductor. P-type refers to the positive charge due to the missing electrons. So where do we use semiconductors? Semiconductors are the best material to use in many electrical circuits, where we have to control the many electrical appliances in everyday life use semiconductors as well, of course. Examples include laptops, smartphones, televisions, washing machines, and so much more. That's it for today. Thank you for watching.
Transistors, and this is actually an i7, and inside all of these are specially made silicon crystals, and actually at a particular level inside the silicon. It's going to have 4 electrons in its outermost, like it's a valence shell, sort of covalent bond between the two. And so in a whole lattice, or like a crystal of silicon, all of these electrons are going to be tied up in these covalent bonds. And so none of the electrons are going to be free to move around, at least not at any kind of normal temperature that we would find this at. And since in order to conduct electricity, we need to have electrons that can move around, perfectly pure silicon like this actually doesn't conduct electricity. And so actually the silicon that we use to make diodes, transistors, microprocessors, and all that sort of stuff actually has some impurities introduced, which is something we call doping. And these impurities allow it to conduct electricity in a particular way. And this doped silicon is what we call semiconductor material, since it's not really a regular conductor like copper wire. But it's also not a complete insulator like something like glass. So one of the impurities that's commonly added to silicon is phosphorus. And phosphorus has 5 electrons, and so it has 1 extra beyond what silicon has. And so if we replace this atom here with a phosphorus atom, it'd still bond to the 4 adjacent silicon atoms just like this, but it would have this extra electron in there as well. And maybe if we replace this with a phosphorus, it would have an extra electron there. And if this were a phosphorus, it would have an extra electron there. And so we have these extra electrons that we're introducing into this silicon crystal. And so we've got the same basic structure, but now we have these electrons that can actually start to wander around a little bit. They're not going to go too far from a phosphorus, but as long as we've got enough phosphorus in here, these electrons might wander around. So this electron here might actually kind of wander over here, for example. And this electron here this electron here might wander over here. And so these electrons can move around. And so because the electrons can move around, this thing is actually kind of a conductor. So if we hooked a battery up like this here, we'd be able to get current to flow, right? Because electrons that come out of the negative terminal of the battery could enter this crystal structure and move around. And there's going to be free electrons here that can be pulled out of this crystal structure and attracted to the positive terminal of the battery over here. And so just by doping this silicon crystal with a few phosphine, we can turn this into a conductor. And so that's one kind of doping, but there's another kind of doping where we use boron. And boron is basically the same as silicon, except that it has one fewer electron and one fewer proton. The things in this crystal structure with boron, we replace this atom with boron, we'd have one fewer electron there. And if this were boron over here, and if this were boron down here, we might have one sort of hole here where these electrons that would normally be like other electrons fill in one of these nearby holes. And so you can almost think of that as if the hole that we're free to kind of move around in here, where electrons would be, that are actually kind of free to move around. In reality, it's the electrons that are sort of jumping into the holes, but I like to think of it as if the holes are moving. And so what happens if we hook a battery up to this? So if we hook a battery up to this, electrons are going to be attracted to the positive terminal of the battery. Negatively charged electrons can be attracted to the positive charge on the battery there. And so this electron here that's maybe close to that battery terminal will go get attracted to the battery and leave a hole behind. But at the same time, electrons are going to be coming from the negative terminal of the battery and be filling in some of the holes that are closer to this side. And then these holes, negative side, so the holes are going to kind of flow this way, or really it's the electrons that are filling the holes and kind of jumping along and going this way, charge to be carried through here. And so in either of these cases, whether we have extra electrons that are flowing through here, or if we have an absence of electrons that leave these holes, that we're able to conduct an electric current. Okay, so there's actually a little bit of terminology here for two kinds of semiconductor material here, one that's doped with phosphorus and one that's doped with boron, and both are able to conduct electricity because they have what are called. So in the case of phosphorus, the charge carriers are the extra electrons, are the holes where the electrons would be. And since electrons are N-type semiconductor, and for negatively charged, because electrons are negatively charged, and this is a p-type semiconductor because holes are, the N and the P refer to the charge carrier, whether the charge carrier is negative or all electrical charge, right? Because even though we have extra electrons over here, for example, the phosphorus atoms have an extra proton as well. Same here with the boron. We have each boron atom has one fewer. So the N-type and the P-type just conduct electrical current through these things. Okay, so where this gets interesting is if we have a single silicon crystal here, N-type material, and half of it is P-type material doped with the boron. So over here in the N-type half, we've got negative charge carriers with extra electrons that are free to wander around. And over here in the P-type, free to wander around. But things get really interesting here at this boundary. This boundary we call the PN junction. The PN junction. And this is kind of what things look like at that PN junction if we zoom in. So let's take it. We're going to have a few atoms over here. And so we've got free electrons that are free to kind of wander. Interesting, because you've got this electron sitting very close to this hole, into that hole. And in fact, that is exactly what will happen, is this electron will find it really tempting to go, these electrons here are going to find these nearby holes. And even, some of these electrons over here might find it kind of tempting for them to go jump into some of these and find those holes. And so a couple interesting things are going to happen here. First, this kind of region of N-type material here is going to, take on a little bit of a positive charge. So there's going to be kind of a positive charge in this atom still is going to take on some extra electrons have shown up and are filling in those extra holes. So there's a little bit of a slight positive charge here. N-type material over here is going to be, this is N-type material over here, is going to be kind of normal, everything just like we described and the rest talked about before. But right at this boundary, a couple interesting things going on. Not only do we have these slight charges separating, but because all of the sort of electrons near the boundary have filled in all the holes near the boundary, we have this region, like right in here, extra electrons. There's no extra holes or no holes over here. And so there's no charge carriers in here. And so we call this the depletion region. Depletion region. And we call it that because it's depleted of charge carriers. Is potentially a bit of an insulator. So that is, it might actually prevent current from flowing from one side of this to the other because we don't have any charge carriers in here that could carry that current. So let's take a look at how that might work. So if we have some N-type material, we've got the holes in here, and we have this depletion region here in the middle. So if we hook this up to a battery side, electrons are going to enter this N region over here. So there's going to be some extra electrons showing up here, and some of them are going to wander over towards this this depletion region in the middle. But when they get to the depletion region, there's cross here, and so you won't get a current flowing. But in reality, actually, if this battery is really of any decent size, there's going to be enough electrons going in that actually they are going to start to get closer and closer to this depletion, or to the boundary, the PN junction. And at the same time, there's going to be electrons over on the P side that are going to be attracted to the positive terminal of the battery, right? The negatively charged electrons are going to be attracted to the positive charge here. And so those electrons are going to leave, and they're going to leave holes in here. And these holes are going to kind of move around. And again, if this battery has got any kind of strength to it, there's going to be, quite a number of holes that get introduced here. And those holes are going to start to move in this direction towards the negative terminal. And so if this battery, actually as it turns out, if it's greater than about 0.6 volts, this depletion region will actually just collapse altogether, and you'll start to get charges that can flow all the way through because you won't have the depletion region in the middle where there's no charge carriers. There will be charge carriers all the way through, and so you'll get a current flow all the way through this thing. But now what happens if we hook the battery up the other way? So what happens if we have the positive terminal over here and the negative terminal over here? So what's going to happen is some of these electrons here are going to be attracted towards the positive terminal of the battery, and so some of these electrons will start to leave, and they'll be attracted to the positive terminal of the battery. At the same time, there's going to be electrons that come out of the negative terminal of the battery here and are going to start filling in some of these holes. These electrons are going to come fill in some of these holes on this side, and so really what ends up happening is in this scenario, the depletion region will actually get bigger or get wider, because these electrons are going to be leaving the N material, and there's going to be electrons that are going to come into the P material as this becomes a little bit negatively charged because of the negative terminal of the battery and fills in these holes, and so the depletion region ends up actually getting wider, and of course because there's no charge carriers in this whole region here, this area is going to act like an insulator, and no current will flow here. Yeah, and so this PN junction here has this really interesting property, right? That it'll allow current to flow in one direction, but prevent current from flowing in the other direction. And so maybe you've heard of a diode, but a diode is this electrical component that allows current to flow in one direction, but not the other. And this is exactly how it's built and exactly how it works. And this is the electrical schematic for a diode. And it's a little bit confusing because you have this arrow that points in this direction here. And that's because the electrical engineers tend to prefer to think about current flowing in a positive direction, so from positive to negative, when in reality it's the electrons that are flowing from the negative side to the positive side. So in a diode like this, even though the arrow is sort of pointing in this direction, the electrons are flowing in this direction. And it's a little bit confusing, but I guess the discoverers of electricity didn't know about electrons. I guess so. I guess Benjamin Franklin got it wrong. When he was saying that charges flow from positive to negative. But it actually turns out that it doesn't really make a difference which way the current is really flowing, as long as we use one convention consistently and stick to it, whether it's positive to negative or negative to positive, because the direction of current flow doesn't really affect what the current does. So a lot of engineers prefer to think of current flowing just this way, from positive to negative, even though really the electrons are going from negative to positive. If it helps, you can think of like the holes flowing in this direction. But again, it's there's two conventions that are completely opposite, and as long as you're consistently using one, it doesn't really matter. But hopefully that's not too confusing. But in any event, this is how diodes work.
Okay, people, we are going to continue with the subject. So we are learning about semiconductors. So the way that a semiconductor is going to function is going to be based on the N, that is going to be the positive charge, and also the P for the positive charge. So we have two types of semiconductors, and typical applications are like diodes. So in the videos, they were discussing about the holes and how the holes are going to be the place for electrons to move. So we have semiconductors through electricity. Let me grab an image for that. Okay. So we have some semiconductors here, like op-amp, like amplifiers, transistors that are going to be switches. Okay. And diodes. Also diodes are going to function in conducting the electrons and not letting the electrons getting back from that. So they have usually only one direction. They are going to have one direction, and there are different types of diodes too. Then we have the capacitor that is going to act like a battery that is going to charge between the plates. Okay, and then it's going to discharge, and that is going to be the process in which the capacitor functions. And the resistor that is has a limited amount of resistance based on these bands. Basado en estas bandas, los resistores van a tener una resistencia limitada. Así que tenemos semiconductores a través de esta pequeña imagen, ¿verdad? Donde tenemos transistores, que son los switches, ¿verdad? Que van a switchar. Tenemos los ICs, que serían acá los componentes, ¿sí? Electrónicos para realizar algo en específico, como por ejemplo un PIC. Un PIC o PIC es un semiconductor que puede ser programado a través de herramientas como la computadora y conectarlo con un programador. ICs, op-amps, que son, van a hacer un cambio en el voltaje también, y van a ser utilizados normalmente para audio, resistores, capacitores y diodos. Okay. Then we have a bigger set of está muy pequeña esa imagen. We have los conductors, wires, semiconductors, like this from the transistors, los diodos y los aislantes. Por acá vemos aislantes a nivel, pues, ya un poquito más grande del tendido eléctrico, ¿verdad? De cómo yo voy a tener no transformadores. A eso se le llama los conductores. Material. All right, electrical magnitudes. So we already saw some of the basic parts for the electric components from the last class. We were here. An alternator, receivers for the bulb, buzzer, belt, an engine that is going to hold the charge, okay, in the circuit, and then the conductors for the wires, cables, and also the symbols. We usually is going to have copper for the conductors. Normalmente va a ser de cobre los conductores. Y bueno, también muchas veces los chatarreros, digamos, buscan el cobre, ¿verdad? So we have copper, and insulators typically is going to be plastic. Para los aislantes normalmente va a ser el plástico, ¿verdad? La manera. Controllers, que eran los IC allá, era de que yo puedo tener desde algo muy sencillo hasta algo muy complejo. Tengo aquí switch, push switch, okay, for normally open, normally close, ¿verdad? Normalmente abiertos, normalmente cerrados, two-way switch, a two-way switch, and double pole switch, and the characteristics for those. Okay, continuing here, look at these pictures. Look at these pictures. Okay. Veamos las imágenes. Ok. Nos dice, definitions for the voltage. ¿Qué cosas, verdad? The electrical magnitudes. ¿Qué cosas se relacionan en todo el universo, digamos, todo el mundo? Voltage is the energy given to electrons to pass through a circuit. El voltaje, la energía dada a los electrones para pasar de un circuito o a través de un circuito. Voltage es esa fuerza que van a tener, por eso a veces se le llama mucho potencial, porque es la fuerza que va a tener el voltaje, ¿sí? Current is the number of electrons every second. Current es la cantidad de electrones que hay en cada segundo. And the resistance is the opposition that some materials offer to the movement of electrical current. Así que la resistencia es la oposición a ese flujo de electrones. Additional information for the measures, magnitudes, voltage, volts, and the symbol is going to be V. Unit is going to be volt. Current as the ampere. And the symbol is going to be the A. El símbolo va a ser la ampere. Va con primero el acento ampere. Resistance, and we have this symbol, a Greek symbol, un símbolo griego, ¿verdad? The resistance depends on the material, the shape, the thickness, and the length. So how resistors work? Vamos a ver un pequeño video de cómo funcionan los resistores.
So I don't have any data to back this up, but I feel pretty confident in saying that the resistor is the most common electronics component in the world. It is used in practically everything. It's used So I don't have any data to back this up, but I feel pretty confident in saying that the resistor is the most common electronics component in the world. It is used in practically everything. It's used in setting operational amplifiers, getting that feedback loop set up, voltage dividers, current limiters for LEDs, and so many other things. They're just everywhere. So we're going to go over that really quick, and we're going to learn more about resistors and what we should pay attention to with them. So the resistor symbol is actually very straightforward. There's the European resistor symbol, and then there's the American, or the more, well, for Americans, more standard resistor symbol, and as you see, they are actually quite similar, so that's pretty nice. However, the challenge comes when you're looking at the actual physical resistor itself. Even though on your schematic they look the same, in reality, resistors look wildly different. So I have here what one would consider the most stereotypical resistor, and this is an axial lead quarter watt through-hole resistor. And this is, when people think of resistors, basically what you think of. It's got the color bands to show you exactly what the resistance is, as well as a band showing the tolerance of this. And so this is the stereotypical resistor. However, resistors come in all shapes and sizes. So I also have here with me a small bag of resistors. Now these are 0603 resistors, and they are absolutely tiny, and they're not even close to the smallest they have out there. The smallest one that I am able to actually solder is an 0402, which is quite a bit smaller than this. And the smallest ones are so small, I wouldn't even try, even using my microscope to solder. They're so small. And resistors also come in the other size. They get huge. My father-in-law makes elevators, and he designs control boards, and he uses these massive brown ohmite resistors to control the flow of electricity when necessary. And when I first saw that, I was still in school, and I did not believe that they were resistors. I thought my wife was just messing with me. But no, you can see resistors in all shapes and sizes. So if you see something and somebody says it's a resistor, they're probably not lying to you, even if you've never seen it in that package before. So don't be surprised if you have some that are through-hole, that are surface mount, that as you saw here, they're chassis mount, panel mount, any variety. Again, since the resistors are so ubiquitous, they are in every package style, every mounting style that you can imagine. So now, the good news is that resistors are very easy to use. They're highly linear as the voltage changes. The current through them is of parasitics. There's a little bit of inductance and a little bit of capacitance, but it's so tiny that most of the time you just completely ignore it, unless you're doing RF circuits. And frankly, they're just very straightforward. So the basis of a resistor is that as the resistor is put into the circuit, the electrons go to it, and it slows that flow of the electrons. It resists the flow of electrons so that you won't have, as an analogy, a resistor is like basically a point where the pipe gets smaller, so the water struggles to get through it. So a bigger pipe means low resistor current or less water flow, using that analogy. Now, the behavior of electricity through a resistor is very easily described using Ohm's law, V equals IR, or voltage equals current times your fundamental understanding of how electricity works. Now, going back to that analogy, you can see that voltage, which is the pressure pushing the water, versus the current, which is the actual flow of the water, would be related to the size of the pipe. So Ohm's law shows that linear relationship and is really, really helpful to get an intuitive understanding of what to do when you're trying to set the current or control the current in a circuit. So when you're choosing a resistor, some of the most important things to figure out is obviously the resistance. That's the biggest one. But you also need to know what the power rating is, how much current and at what voltage is going to be through and across this resistor, because too much power and too small of a resistance, again, this is a quarter watt resistor, you try and put too much power through this thing and you are going to have some serious issues. That large resistor in the picture from the elevator controller, that obviously is more in the tens to hundreds of watts, where these are more in the quarter to tenths of watts. So again, figure out the resistance, the power dissipation capabilities. You also want to know the tolerance. Most resistors like this, their tolerance is 5%. You want to pay more to get more like 1%. You can even get down, I think, to 0.01, 0.001%. Of course, the price just keeps on ramping up. And if you don't need that sort of precision, you usually want to design around it and you don't want to pay for it. And then finally, the thermal coefficient. You want to make sure that as you're in a hot place or a cold place, it's not going to throw off the resistance of your resistor, because you could have your circuit in the Antarctic and it acts one way, or in the Sahara and it acts another way. You want to make sure that you either have a resistor that doesn't have an issue with that temperature coefficient, or again, design your circuit so that any sort of deviation from that ideal resistance is not a big deal. Finally, as I mentioned earlier, resistors are great in that they're very linear and they don't get affected by frequency. However, again, in reality, all of them have a little bit of inductance and a little bit of capacitance. So if you're going to be doing a high frequency circuit, you want to be making sure that your resistor has minimal capacitance or minimal inductance, or at least that you know what it is so that you can take that into account when you're designing your circuit. And that's really it. Resistors are very straightforward but incredibly powerful, and for the most part you can just drop them in, and it's not until you start doing more production level designs that you need to worry about exactly all of those tiny little details. But for most just prototyping hobbyist work, you can just buy a package of these things and use them in almost every single project you have, and then from there change to what you need. And if you're going to start doing your PCBs, you can start buying these tiny ones so that you can make your circuits even smaller. All right, that's it for now. Check out our site, circuitbread.com. If you like this video, leave a like, and we always want to hear your thoughts, so leave it in the comments below.
Muy bien, así que esa es la manera de cómo están construidos, ¿verdad? Los resistores o resistencias que les podemos decir, y vamos a ver un poquito de las bandas, de lo que hablaba, y también la tolerancia. Bueno, aquí hay algunas de ejercicio. Resistor, vamos a poner. También se le llaman las bandas de ejercicio. Resistance bands.
In this video, Ohm's law and how to pick a resistor to limit current in an LED circuit. In previous videos, I talked about how voltage can behave like a pushing force, pushing electric current around a circuit. But in one example, I connected an LED straight to 7.5 volts. Way too much current flowed and the LED blew up. So you can see how it would be useful in something that could tame the flow in a controlled way. That device is called a resistor, and here are some examples of what resistors can look like. We've got a very basic resistor over here, which is the kind of resistor that most hobbyists would use at home when constructing circuits. And over here we have a tiny surface mount resistor. This is something that you'd expect to see in a small device like your phone. And this big resistor is the type of thing that you'd use in a large power supply. So how do these resistors work? It's jumping from atom to atom all at the same time like a conga line? The atom's in a material, and this is because sometimes they'll bump into an atom that's in the way, and some